So today we're going to look at a couple more examples of working with these force systems in equilibrium. And really, these are going to be more of your real world examples. So this first one that we're going to look at, it is a little bit more complicated. We're going to have to draw multiple free body diagrams, but this is something that you might encounter in real life, where we want to determine the maximum weight that we can put in a bucket in this system so that no single cable exceeds 100 pounds of force. So it's if we're given in real life a rope and we say if we put any more than 100 pounds of force on this rope, it's gonna break. That's the scenario that we're looking at. We want to know what is the maximum that we can load up this bucket. How many rocks, how much weight can I put in this bucket so that none of my cables snap? So we want to determine what the tension, what the maximum weight can be in the bucket so that no single cable has a tension greater than 100. So this is more like reverse engineering a problem rather than straight solving. But we're still going to set everything up the same way, right? So again, the way I always start these is we have to set a coordinate system. So I'm going to set my coordinate system as the traditional X and Y. And I will say that sometimes when you see these coordinate systems listed, when we set our equilibrium equations, you may sometimes see people write it like this, where we say the positive direction is to the right when we sum our forces in the X direction. This way we know that what's positive is going towards the right. It's the traditional system, but you may see that what's positive is going towards the left. Summation of X. This might be in a case where all of your forces are pointing to the left, so you want to say, instead of using negatives, I want to go ahead and just make everything to the left, make that a positive. Don't worry about the signs. So there are reasons to flip around your system. You may have maybe a system that kind of sits on its side rather than a traditional XY axis. So you might have something that looks like this, and you're like, well, if this is a 90-degree angle, then I still want, then I'll make this the positive Y direction and this the positive X direction instead of the traditional system. But for now, we're just going to keep using and keep looking at the traditional XY system that we know and love because it's a little bit easier to work with, right? It's what we expect. And so as we're learning this, we want to kind of keep things as simple as possible. I'm going to say my positive is in the positive x-axis direction. Summation of those forces is going to equal 0, right? We're in equilibrium. And then you may see it written the positive upward direction of y, summation of forces in the y direction equals 0. So sometimes you will see these prefixes on here. It really helps with setting the coordinate system. So we have this. Let's go ahead and draw our free body diagrams. So I'm going to need 2 free body diagrams. And the way that I know that is that I can see these 2 main circle points. At every single point, I could draw a free body diagram. For example, if I drew one at point C, all I would have is that reaction coming, is that tension coming off of the wall, and then also what it's putting back onto the wall. We're going to learn a little bit more about that later. So for now, we just say it's fixed to the wall. And we're just going to look at these points B and E. So if I draw my free body diagram at my point B, I draw it somewhere where I can keep it. All right, I'm going to make my one at point B in green here. So at B, I have the tension in cable BC. I'm just going to call it FBC for now. I have the tension from A to B in that cable. And then I have going down this tension from B to E. You don't have to use this naming convention. Name it in a way that makes sense to you. So you might call this, you could call these T's instead of F's if you like noting that it's a tension force. Tension just means that it's being pulled taut, right? It's not in compression, it's not being squished. So the opposite of that is tension, which we show is the force coming off of something, out of something, because it's pulled apart. It's being stretched as far as it can go. The forces are pulling things apart. That's all we mean by tension here. You can label it as a force. You can label it as, if I didn't want to call this FBC, I could call it FC for the tension in that cable. You could even just call it BC if you wanted to. You don't even have to call it a force necessarily. Whatever naming convention kind of makes the most sense to you. But this is the naming convention that I'm going to stick with because it's easiest for me to keep straight. I can see exactly each part of it, right? Force in cable from B to C. Right, it lists out every part. I'm not going to be confused at any point if I use this naming convention. Alright, I'm also going to go ahead and put my angles on here just for my reference. I'll do those in pink. So this guy is 30 degrees. And then this guy we see has a 3, 4, 5 triangle. 3, 4, 5. So I'm just noting those in my free body diagram here. And I can go ahead and set up and solve with my equilibrium equations. So I can say, in the positive x direction, if I sum these forces, it's going to be 0. And I'm going to have the x component of this force, it's entirely in the negative x direction, so negative FAB. And then these two forces both go in the positive x direction, so they'll both be added, plus the x component of FBC is going to be FBC times this adjacent cosine 30, because we're looking at this component here, and if we take the cosine, that gives us the adjacent to the angle value, cosine 30, plus this value. Again, you can find the angle if you want, but we can just use the ratio. We can use the x component of the ratio over the whole force itself, right? So that is 3/5. That is the ratio of the x component to the overall. 3/5 FBE. So now let's go ahead and look at the y equation. If I look at the positive direction of my y is going straight up. Summation of the forces in the y direction set equal to 0, right? This is our equilibrium equation. I can ignore FAB. I'm actually going to do this in blue. I can ignore this guy because he's all entirely in the x direction. And then I can look at the y components of FBC and FBE. So if I look at these, my FBC is in the positive y direction. That's this component right here, which is going to be FBC sine 30. FBC sine 30, because opposite of the angle 30 is this component here. Minus, because our FBE is going down in the negative y direction, minus FBE. Again, we can use this 3, 4, 5 ratio triangle. The y component here is 4 to the ratio of the overall is 5. 4/5. So what I end up with here is 2 equations, but 3 unknowns, which in a traditional problem is how I'm going to know that I need another free body diagram. This is how I know I need multiple free body diagrams. And I might have been able to save myself some pain if I actually would have started with this one at point E instead of the free body diagram at point B. But that's okay. Sometimes you do things out of order. Sometimes it, takes a little longer to work through the problem if you set it up in a little bit different way. So we could have set this up more efficiently by just doing point E first. But it's okay because we are still going to get to the right answer. It's just going to take us a little longer than if we had started with point E. And a lot of these problems are going to work like that. If you end up looking at a solution guide or any keys or anything, you might see that they had done some things in a different order or in a different way than you had done them, but you both still got the right answer. And that's okay. There are sometimes just multiple approaches to a problem. It's just about figuring out the way that makes sense to you to get everything to work out. Some ways are less steps. That doesn't make them any more correct than another way, as long as you're still arriving at the right result. So I'm going to move all of this to the side. We're going to bring these back in a minute, but let's go ahead and do our free body diagram at point E, because that's really going to get us to the heart of this problem, which is that pesky to no tension more than 100 pounds, and we're going to look at how to deal with that. Okay, let's do our free body diagram for point E now. So looking at point E, what I have is I have my bucket. I don't like this color. I don't want that. What I have is I have my point E here. I have the weight of the bucket coming off of it. This is the thing we're trying to find, right? We don't know the weight of the bucket. We want to know the max weight of the bucket. And then I have cable, the force in cable DE, and the force in cable BE, where I have this angle here is 30 degrees, and then this triangle over here was given as a 3, 4, 5 triangle. So I can apply the same equilibrium equations that we've been applying. My coordinate system stays the same throughout. This is very important. Do not change your coordinate system just because you're moving to a different part of the system. The coordinate system is for the entire problem, the entire thing that we're looking at. So we're still going to be using, in the positive x direction, summation of forces. It doesn't include our weight, right? So this equals 0 because it's an equilibrium. It doesn't include our weight because this is entirely in the y direction. So in our positive x direction here, we're going to have FDE cosine 30. It's in the positive x direction. So it is a positive, and it is cosine because it's adjacent to that angle. FDE cosine 30. And then we'll look at FBE, which is in the negative x direction. So it's going to be negative FBE, and then we're going to use this ratio relationship. It's 3/5 is the ratio of the x component to the overall. So this is our equation. This is our first equilibrium equation. Let's set up our y equation. In the positive y direction, summation of y forces equals 0 equals, I already know we have a negative w. This is all we have in the negative y direction. Negative w plus, these other two are in the positive y direction. This component is FDE times sine 30. FDE sine 30, because it is opposite of the angle. And then we will use our ratio triangle again. It is, the y component is 4 over the total of 5, plus, in the positive y direction, FBE times 4/5. Now this is where the problem gets interesting, because we know that no single cable can develop a tension greater than 100 pounds. And the way we're going to do that is we're going to solve every cable equation, every force, in terms of W and see what the greatest relationship is. And then we're setting that one equal to 100. So what we want to do as we go through this problem is that we're going to leave W in here as a variable still. And we're going to set up many different equations with relationships of the force of the cable to W. So for example, Let's go ahead and set this up as if we knew what W was. Kind of solve the systems of equations as if we knew what W was. So if I were to do that, I would come back and I'd look at this, right? And I can rearrange this equation. So I can say, you know, FDE equals FBE times 3/5 divided by cosine 30. And if I wrote that in just numerical form, I would have FDE equals, actually I'm gonna write this the other way. I'm actually gonna multiply over the cosine 30 and divide by 3/5. So I want I want to look at FBE instead. FBE is going to be, if I punch this into a calculator, FBE is 1.44 times FDE. So I have this relationship I found just by basic algebra that I am going to plug in to this equation over here. I'm going to plug him in, right down here into this guy. So this would be just as if we were solving a traditional system of equations, a traditional problem. This is how we would approach this. So if I plug this in, I plug it in here and I'm going to get, I'll write this in blue, I'm going to get negative W plus FDE sine 30, which sine 30 is just a half. I'm just going to write a half. Plus 1/2, or times 1/2, plus 1.44 FDE, just that straight substitution, times 4/5. So if I combine these two together, right, these two are the same, these are the same variable. If I combine these and rearrange this equation, I get FDE equals 0.604 W. So this is the relationship that I'm looking for. I want to get this type of relationship. My force equals something times W for every single one of these components, for every single one of these cables. I want to get this relationship. So I'm going to put it over here in purple, that my FDE is 0.064 W. And what I'm looking for is I'm looking for the one with the highest value in this part of the equation, the highest coefficient here in front of the W, because that's going to be our limiting factor, right? That's going to give us what the maximum value of W can be if we set this value equal to 100, right? Because we're going to be dividing this out and it's going to give us the absolute maximum that W can be, so that this number, this force in the cable, does not exceed 100. So that's why we're going through and we're finding these for every single cable. So I can come and I can substitute this relationship back into this FBE equation, right? So I would get FBE equals 1.44 times 0.64 W. And what does that give me? That gives me, write it down in the corner here, FBE equals 0.872 W. So now I have these two relationships. I'm going to go back into those equations we did at the very beginning for the free body diagram at point B, and we're going to plug them in and continue down the line, continue solving for what the tension in every single cable is. So let's go back to those equations that we did earlier. So these were the equations that we had worked on and established earlier, and if we hadn't done them at the beginning of the problem, then we would be doing them now. So we didn't save much work either way, it was just a little more intuitive if we would have done point E first. But either way, we would have done the free body diagram at point B, and we would have found these equations. And so what we can do with these equations now is we can substitute in these two relationships that we found into these to get our relationships with W. So for example, I'll take the bottom guy here, FBE equals 0.872 times W, and I'm going to substitute that in to our top equation here. This is our Y summation, Y component summation, so that I get FBC times sine 30 minus 4/5 times 0.872 W equals 0. So now I can just add this component over to the other side and divide by sine 30 so that I get FBC. If I punch into a calculator, 4/5 times 0.872 divided by sine 30, I get 1.4 W. So this is our highest contender so far, and there's one last one we need to check, right? There are a total of 4 cables in this problem. You have AB, BC, BE, and DE, right? So we've checked 3 of the 4, so we'll go ahead and substitute in this last one into our equation here, along with FBE in our equation from over here. So we're going to substitute these into our equation, and we're going to get, sorry, this is in the way. I don't want this here. Let me write this in down here. That our equation is now, if I add FAB over here, I can say FAB equals FBC was 1.4 W times cosine 30 plus this term is 3/5 FBE was 0.872 W. So now I just combine these and I get that FAB equals 1.73 W. So this is our highest contender. And if you're not sure which one of these 4 equations here, whether you use this equation or these 2 equations over here, which cable you need to be checking to see what the max weight could be, we could plug in 100 into all of these equations, right? The maximum they can be is 100. So I could put in 100 into each of these and divide it out and see which one gives me the lowest weight that works for all of them, right? You don't want to pick the highest weight because then it's exceeding for some of the other cables. Other cables are going to be exceeding 100. What you want to pick the lowest applicable weight, and that gives you the maximum weight that is allowed, right? Does that make sense? This idea that if I were to plug in, let's say, so I put in this equation, make some room for myself here, move all of this, right? So if I put in my FAB, 100 equals 1.73 W, then I divide each side by 1.73. 100 divided by 1.73, I get a weight of 57.7 pounds. Told us everything was in pounds. We're assuming pound is a force. Pound force here. So I get a weight of 57.7 pounds. But if I plugged it into one of these other equations, and I said 100 equals 1.4 W using our FBC equation, and I divide by 1.4, then I get a weight of, let me plug that into my calculator, 100 divided by 1.4 gives me a weight of 71.4 pounds. But if I plugged this weight back into this equation, and I said 71.4 times 1.73, that would give me a tension in this cable of 123 pounds, which means I'm exceeding that 100-pound limit. So that's why we want to pick the greatest ratio here, which is this FAB, and it spits out the smallest amount of weight that works for all of these cables. And again, you can plug them into the equations over on the left here to cross-check. But this is our answer. This 57.7 is the highest amount of weight that we can put on the cable, the 100-pound force cable going through DE. This is the highest maximum weight that we can put into the bucket and have no cable exceed 100 pounds. So it was a longer example. It may have been a little confusing. Try to work through it on your own to understand. And we'll have some homework problems like this, so hopefully it should make a little bit more sense. But this is really the real world application of this, right? We don't want any of our cables breaking. We need to know what the maximum load we can apply to something is. So this is the application of statics, and we're going to see more of this and start working in 3D in the next video, because that's the world that we're actually going to be working in.